Hello, my name is Judah Rosno, and this is my presentation for Case Study 7. The objective of this project was to redesign an ESC assembly to survive a 15-second power burst. The design had to meet two strict constraints, keeping the peak transient temperature below 100 degrees Celsius for safety and adding no more than 15 grams of mass to keep the drone light. I successfully concluded this by keeping the peak temperature to 86.9 degrees Celsius while only adding 6.45 grams. First, I ran a baseline transient simulation on the bare silicone chip. This silicon chip has a thermal conductivity of 124 watts per meter squared Kelvin, specific heat of 700 joules per kilogram Celsius, and a mass density of 2,360 kilograms per meter cubed. The thermal loads included a 15-watt power input per MOSFET body set to a 15-second active time curve, an ambient temperature of 300 Kelvin, and a convection coefficient of 25 watts per meter squared Kelvin, all on every face except the bottom face. Due to the basic geometry of the MOSFET, mesh refinement and convergence were achieved with a coarser mesh. As expected, the base chip failed to test, reaching a peak temperature of 154.96 degrees Celsius, which well exceeds the 125 degrees Celsius failure threshold. To verify my solution simulation, I compared the SOLIDWORKS results against my theoretical lumped capacitance calculations. My theoretical solver predicted a maximum temperature of 157.168 degrees Celsius. Comparing this to the simulation's result of 154.96 degrees Celsius yields a percent error of less than 2%. This quantitative comparison proves the model is mathematically stable and correctly reflects the boundary conditions. For the iterative design modification, I added an aluminum 6061 heat sink to the top of the MOSFETs. To add this to the assembly, I didn't use any thermal paste because thermal paste would aid in heat transfer. So in my simulation, I did not add an interaction. For similar reasons, I lowered the convection coefficient to 5 to make sure that the heat sink was adequate in the worst conditions. I went through several iterations of fin width and amount. I came to this final design because it was able to keep the MOSFET cool while not adding an excessive amount of cooling. The mass properties report confirms the new aluminum heatsink adds 6.45 grams, keeping us safely under the 15-gram limit. After rerunning the simulation with the same temperature initial conditions and adding convection to all exposed faces of the fins, we redesigned assemblies peaked at just 86.9 degrees Celsius. The temperature over time graph clearly illustrates this improvement. The baseline shown in blue spikes dangerously high, while the redesign in red plateaus safely under our 100 degrees Celsius target. In conclusion, this thermal management solution works theoretically, but our next steps will require experimental validation to account for real-world discrepancy. Thank you.